This conference will now be recorded.
So very good evening, students. Today we'll be discussing about standing waves and normal modes, beats, etc. This is very interesting topics because the principle of all the music instruments, organ, pipe, sitar, violin, etc. are based on this principle of normal modes created at various situation. Okay, so those things like upon okay, we'll see as you go along with this lecture. So let's start our class today. So what is standing wave or stationary wave? Stationary and standing are the same. Here main thing is, let me just tell you the background why this word standing wave is coming over here. Actually, if you look in the previous classes we have discussed, we have discussed about traveling wave or progressive wave. Progressive waves, okay? And this kind of traveling wave, they are represented by the displacement of material element in the medium when the wave travel. So that is denoted by some kind of sign, some sine or cosine function. So a sine omega t minus kx if it is moving in the positive x direction, and it has no boundary. It can go up to infinity, okay, in both sides, positive and negative x direction, both sides. So if I want to write this is actually moving towards positive x direction from origin to infinity, we can say. And this is another traveling wave. Suppose this is y1, this is y2, which we can consider sine omega t plus of kx. So this means that the wave is traveling in the negative x direction, okay, in the negative x direction. So these are actually traveling wave. You can see in the argument of the sign, we have two things, omega t and minus or plus kx, okay. So this is the sign of traveling wave. Sign of traveling wave in any equation like this, if we have only omega t, that is not traveling, okay, that is not traveling. Or if we have only kx, that is not traveling. If we have both this argument, then it is denoting traveling wave. So this you have to remember, which we'll be using here. So we have discussed traveling or progressive wave in the previous classes. Today what we'll do, we'll discuss about standing wave or stationary wave. That means in a particular region of the medium, the waves will be confined, they will not move on either sides, okay. So in this case, if you want to have traveling wave, you must have two boundaries, okay. You must have two boundaries for the wave to be created. So if you have some air column and you are just inducing some sound wave, so the sound wave will see, first it will come, suppose it will go in the right hand direction, suppose, and this will act as a wall, fixed wall, and that gets reflected back, okay, reflected back, and this reflected wave and this original wave, these two are actually identical, but only thing is they are traveling in the opposite direction. Identical in the sense they have same angular frequency, they have same speed, and they are moving in the same medium, okay, etc. So, and obviously they have same amplitude because it is just reflection of this, okay. Only thing is direction is different. So such two waves, if they interfere, if they superpose, then standing wave will be produced. Okay, let us see the definition. When two identical waves of same amplitude, same frequency, traveling in the opposite directions with the same speed along the same path, superpose each other, and resultant wave does not travel in either directions and is called the stationary or standing wave. I hope the definition is clear. To make you again clear, I'll just give you simple example. Suppose I have two rigid or fixed support in which I am just tying or fixing a string. Fixing a string. Upon fixing a string, if I just pluck it and leave, pluck and leave, or just give a hit, just hitting it here, then what will happen? There will be a disturbance created or wave created, which will that will be obviously a progressive wave. So that will be created. Okay, let us say the wave is created and it is traveling like this. Okay, traveling like this. Okay, so this traveling wave, I'm sorry, the amplitude is not same both places. Okay, I'll just redraw. Oh, sorry. Okay, maybe now it is okay a little bit. Anyway, suppose this is the wave which is produced at this place and it is traveling in the positive x direction or in the rightward direction, suppose. Then what will happen? It will go all the way up to here. At this fixed end, we have already discussed reflection of waves. If this is a fixed rigid point, then here what will happen? This wave will get back, reflected back. And what will be the phase between the original wave and the reflected wave? The phase difference will be pi. That is what we have seen, or they will be 180-degree out of phase. Okay, so that is what we have learned. Okay, so this is the reflected wave. This is suppose traveling in the opposite direction, and when they superpose, they will create a standing wave. Standing wave means, look, you can see here itself a standing wave has been created. Standing wave means you will have some places, some element of the string will be vibrating with maximum amplitude, and some places the medium or the element of the string will not at all move, okay. They will have zero displacement. You can see that. So this place, you see there is a maximum displacement and here the zero displacement. Okay, this is what actually the characteristics of standing wave. Some element of the string will be, see, maximum displacement, displacement displacement, and here it is zero displacement, okay. So this is the characteristics of standing wave. You might be thinking, sir, how do I know standing wave? This is the characteristics. So some places the particles of the medium will have maximum displacement, and some places the particles of the medium will not at all move, not at all vibrate, not at all oscillate. So those points where the medium is not at all oscillating, that these points are called, these zero displacement points are called nodes. These are called nodes. Oh, I'm sorry. Okay, so my mistake I have. So these places are called nodes. Nodes I am denoting here as N. So look, there are nodes here. You have node here, you have node here, and here. So you have node here, you have node here, node here. Node means where the material element in the medium is not at all oscillating. And see, where there is the particles, where the particles have maximum displacement, those are called antinodes. So we have learned two things: nodes having zero displacement, node actually points having zero displacement, and antinodes, just opposite to nodes. Antinodes here actually points. Antinodes means points of maximum displacement. I hope it is understandable. Maximum displacement. Maximum displacement. So this places, see this here, the material particles or the element of the string is displacing maximum. So that's why these points are called antinodes. These lobes, these are called lobes also. So these lobes are actually of, these are called antinodes. Okay, these are called antinodes. All right. So when you see there are nodes and antinodes, then you can see this is actually the standing wave. So in the standing wave, you know what will happen? In the standing wave, let us go with the string itself. So the wave which was going, sorry, one side, left hand side, okay, so that will get reflected, okay, like this. So the one which was going towards right will get reflected back as this, and they will interfere. So these two will interfere to give you some overlap of superposition of two waves. So further, see, these waves are actually progressive wave. They are actually traveling. They are individually traveling, even though they are actually producing a new wave that is called standing wave, which contains nodes and antinodes. And those nodes and antinode points, so these points are actually not at all moving. These points are not at all moving. Neither the node nor the antinodes are moving from. See, so nodes cannot become antinodes anytime. Okay. So these 2 points actually they are not moving. That's why it is called standing wave. Okay, that's why it is called standing wave. Why? Nodes are not moving, neither the antinodes are moving. So that's why it is called standing wave or stationary wave. Now see what will happen. So these waves will be actually going back and forth. They will go and get reflected back. Like see this wave which is actually going towards the right hand side, it will get reflected as this. They will superpose, and again this left going wave get reflected back again as some other wave. Okay, so get reflected like this. Okay, the one which one going right hand side, that will get reflected back like this. Okay, so this is the way. In this way actually there will be like numbers of waves going back and forth between this boundary, and they will like the original wave and the reflected wave, they will superpose to create one standing wave, and again those two will again like get reflected back from both sides and then again superpose to give you standing wave. So this is the way this is actually a continuous process. It will go on happening. It will go on happening. So there are actually, so you can see, now we'll see what are the necessary conditions to have this kind of stationary wave. There are actually few necessary conditions, even though I have already told, but still I just want to point out. First of all, what are the necessary conditions? Any two independent two independent waves cannot cannot form stationary wave. Okay, cannot form or constitute stationary wave. First of all, you should remember this, and let us standing wave. Standing wave or stationary wave. Let me tell you what it is. See, I can take any arbitrary progressive wave, two progressive waves. Okay, suppose this is one, and another one is, these are two arbitrary, even though they are, suppose this is moving in this way, right hand direction, and this is moving in the left hand direction. Let me take some descent waves like this. Suppose it is moving in the rightward direction. And some other wave which has much bigger amplitude, okay, and frequency also different. So these are two independent. They are not at all actually uh, dependent or related to each other. They are independent. If this kind of two waves, these two independent waves superpose, they will not give stationary wave. No stationary wave. Why? Why is it so? Because see, you should have nodes, antinodes, nodes, antinodes, right? So that is what you should have. But see, if these two waves are superposing in opposite phase also, because of this amplitude difference, see, you will not get node anywhere. You will not get node anywhere. Anyway, you will get antinodes, but you will not get nodes if the amplitudes are not same. If the frequencies are not same, then nodes and antinodes will not be created. Actually, they will not be sharp. Okay, so I hope you have understood this. So nodes and antinodes are the characteristics of standing wave. Those will not be created unless the waves are related to each other, and in fact, both the waves. So then what kind of waves will help you to produce stationary wave? Any wave, any progressive wave, and the wave, okay, and the reflection of the same wave, and the reflection or reflected wave of the same progressive wave, same progressive wave. I hope you have understood. From the strings example itself, you can understand. See, some wave is created and then that is reflected back. The same wave is actually reflecting back. That's why they create standing wave. Okay, so you need actually the same wave and its reflected wave to get standing wave. That is what is first point, and obviously that is the main point. Okay, so it should have a finite boundary. So To produce standing wave, a finite medium or okay, a finite medium, not infinite medium like progressing wave. Finite medium, finite medium with two boundaries you require, with boundaries is required. Okay, is required. So to produce stationary wave, a finite medium with boundaries, at least two boundaries. Okay, two boundaries. Let us say two boundaries is required. That is another point. So these are actually main points. Obviously, medium has to be continuous. Okay, and the waves actually have to travel. Even reflected wave, suppose the reflected wave is traveling this way and some other reflected wave is traveling this way, they should actually overlap, they should move in the same path. Okay, they should progress in the same path, should move. Okay, waves should move, waves should move along same path, along the same path, but in the opposite direction, but in opposite direction. Okay, and obviously the waves have to be have, like they should have same amplitude, same frequency, same speed, and same amplitude. Okay, so fourth point would be that point. Okay, all right, now we'll see there are actually uh okay, so before I go there, I'll tell you two things. There are actually two types of types of standing waves. What are those? One is type, transverse standing wave, and longitudinal standing wave. Longitudinal standing wave. Okay, these are two types of standing waves. Okay, so when two identical transverse waves will interfere, okay, traveling in the opposite direction, obviously, when two identical transverse waves traveling in opposite directions overlap, a transverse standing wave is formed. For example, transverse stationary waves are formed in a sonometer Meldis experiment. Okay, so sonometer transverse. So example of transverse standing wave in sonometer. Okay, in sonometer, and then Meldis experiment, this kind of standing waves are created. Similarly, when two identical longitudinal waves are traveling in the opposite direction and overlapping each other, they will produce standing wave, and those standing waves are called longitudinal standing waves. For example, organ pipes. Organ pipes. In organ pipes, then in Kuhn's tube. In these places, actually, in organ pipes, longitudinal standing wave is created. In sonometer, transverse standing wave is created or produced. Okay. Now we'll try to understand graphically how this formation happens. Actually, I have already told these things. I'll tell you here. So actually, you'll see when in this figure you can see there are three waves are shown over here. One is this deep black lines, but line is actually not continuous line. Okay, discontinuous but deep black. That is one wave which is traveling in the opposite direction, in the leftward direction. This one. Okay, so this one is traveling in the leftward direction, and you can see the dotted line. Okay, so this wave, there are two progressive waves here. One is traveling in the opposite left hand direction. Another one, this one is traveling in the rightward direction. Okay, now look what happens if I see any time. Suppose I just see at any time t is equal to 1/10 of the time period, then we see that these waves are actually they are not in phase, they are actually differ by some phase angle. Okay, they differ by some phase angle. They are traveling in opposite direction, but they have some phase difference. So such two waves, when they overlap, you can see this is a resultant wave. So this is a resultant wave. This is not a standing wave. You can see this is still a progressive wave. This is still a progressive wave, and you can see if the right hand side is not having any closed boundary, so it will propagate. Okay, it will propagate. Now you can see further point over here. See these two waves. These two. So which one is now this one? Okay, let us see this one itself. So now this wave and this waves again, they are having some greater phase difference. That's why you can see the amplitude of the resultant wave is actually decreasing. You can see it is decreased because the phase difference has increased between them, right? But still it is not 180-degree out of phase. They have some phase difference greater than the t by greater than a time t by 10. Now phase difference is greater. That's why amplitude of the resultant is also less. Now you come to this time, like when the time is 3t by 10, this time you can see these are actually going opposite phases. Okay, they are going in the opposite phases. Okay, they are going in the opposite phases, but not exactly, still not exactly 180-degree out of phase, but exactly you can see still. That's why still you can see some places, actually some places you can see there are amplitudes are less, some places amplitude are more. So here see these two guys when overlap, because they are in overlapping in opposite phase, almost opposite phase, you can see this is this is actually going to be node. When these two are actually meeting in phase, so they are actually creating antinodes. Here you look, they are meeting out of phase here, so there will be nodes. This is antinode. Again, here is node. Okay, node at this place. I'm sorry, this is antinode. They are so this is another nodes. These are nodes, and these are antinodes. Okay, antinodes created at this place. If you see, these are actually meeting in phase, so that's why this will be antinode. This is anyway node. You see the resultant wave which has displacement 0 over here, maximum over here, again 0 over here, because these two waves are actually meeting in opposite phase. So this is how standing wave will be created. And if you see again in as time passes, you will see some see actually not only two waves, there will be numbers of waves, because these waves are going back again, coming like going to the other direction and reflected back. So there will be many main waves and reflected, they are corresponding reflected waves. There will be many waves, such waves. So some waves will be actually meeting in phase also. In that case, you will get maximum displacement. Look, these are maximum displacement point where they are meeting in phase. And you look here, they are meeting out of phase. So these places will be and nodes. These places they are meeting out of phase, so they will create a node over here. And since the phase difference is again further at this place, phase difference is very less. That's why the amplitude actually is increasing. Okay, these places they are almost meeting in phase, so that's why their amplitude, resultant amplitude, is more compared to the previous curve. Okay, so this is how standing wave created. Okay, and you can see here, or better I'll draw, or from here itself you can see this is a complete wave. This is a complete wave. So this is half of the wave. So this is the total wavelength. If the wavelength is lambda, so then this is the half of the wavelength. This length is half, and again this length is also half of the wavelength. Okay, so that's why lambda by 2, lambda by 2. You can see that the distance between two nodes actually is lambda by 2. Okay, they are separated by lambda by 2. So two consecutive two consecutive nodes are separated by lambda by 2 distance. Okay, similarly, if you look here, the antinodes also, they are also separated by, suppose this is antinode, this is antinode, these are, okay, better to go with this one. Okay, this is antinode, and another one is here. Okay, so they are also actually separated by half of the wavelength distance. Okay, they are away from each other by half of the wavelength. Okay, half of the wavelength. So nodes and antinodes, both we can say two consecutive nodes or antinodes. Antinodes are separated by lambda by 2 distance. So that this is what we can say from here. Now we'll see the analytical treatment. Analytical treatment means, suppose I'll just take, suppose there are two progressive waves, two progressive waves, progressive or traveling waves, y1xt and y2xt, traveling in the opposite direction, traveling in the opposite direction, direction, directions and overlap with each other. With each other. So what will be the case? How do you find out mathematical expression for a standing wave? So y1, suppose this is traveling in the positive x direction. Y1, a progressive wave which is traveling in the positive x direction. That can be written as, suppose A is the amplitude, sine omega t minus kx. This is traveling in positive x direction. Okay. Y2, with the same amplitude, we have to get same amplitude, same frequency, but traveling in the opposite direction. Traveling along a negative x direction. Okay, these are two waves. Now, according to principle of superposition, we have to find out the expression for standing wave, because upon superposition only the standing wave will be created. We'll just try to use this space. So superposition principle, what it is says, what it says, the resultant wave will be the amplitude of the or the displacement of the resultant wave will be the algebraic sum of the displacement created by that wave, okay, individually here in this case. So y1 is the displacement of the, these are actually displacement, as you know, displacement of the medium when the wave, a traveling wave, is traveling through the medium with frequency this and propagation constant k, amplitude a. Now if we want to add this to, so what we have, a sine omega t minus kx plus a sine omega t plus kx. So when we have a trigonometric identity. When we have sine c plus sine d, this identity is actually connecting you. See, summation of sine c and sine d, this will be actually expressed in terms of multiplication. How? 2 into sine c plus d by 2 into cosine of c minus d by 2. So this is the formula. So in this case also, you look, the amplitude is same, so I can just take this as common. So I have this, if you say this is c and if you say this is d, so what we can write from here? So 2 sine a plus b. So this is omega t minus kx, this is omega t plus kx. So kx go off, right? Kx will go off. Okay, so kx will go off and you will get omega t, 2 omega t by 2. So that will give you sine omega, 2 sine omega t, and cos of, see, cos of c minus d. C minus d means this minus this. So look, omega t will go off and cos of x, kx you will get. So this is actually the expression for the resultant wave upon superposition. I'll write in freshly before I discuss anything else. Let me keep this in bracket and this as time varying term, this one. Okay, let me write in phrase. So what we have got, so I had taken y1 as a sine omega t minus kx and y2 a sine omega t plus kx. So resultant wave we have got applying superposition principle. What we have got, 2a cos of kx and this is sine omega t. Okay, so this is what we have got, and this expression is actually an expression for a standing wave. You look, in the beginning itself I have told, when you have this argument with sine or cosine, then it will give you a traveling wave. These are actually traveling wave, both are traveling wave, because in the argument sine both time and space is there. But in this case, you look, this is acting as amplitude to a cos of kx, and this is time varying term where you don't have space varying term. So this will not give you, so this is an expression for, standing wave. This is not an expression for traveling wave, because you don't have this kind of argument for the cosine or sine. See, this amplitude, you can see there is a difference. Here the amplitude is constant for a traveling wave. So for a traveling wave, amplitude is constant, and it does not vary with space, does not vary with space, with space. Okay, with position. But in this case, look, this k x means what? So for this standing wave, what is happening? Amplitude is different at different position of the medium. Amplitude is different at different positions of medium. We'll see where it will be maximum and where it will be minimum. Okay, here we'll see where it will be maximum and where it will be minimum. See, we have amplitude, expression for amplitude to a cos of kx. Okay, so we can find out where the amplitude will be maximum and where the amplitude will be minimum, or condition for having nodes. Maximum amplitude means antinodes, and minimum or zero amplitude means nodes. So look where we will get the nodes, position of nodes. Okay, where the positions of the nodes when a will be equal to 0. And how it happens? If the kx, this term, is becoming n plus, like odd multiple of pi, right? Like odd, yes. So pi by 2, then 3 pi by 2, etc. So where n is equal to 0, 1, 2, 3, etc. At those places, the nodes will be created. So first node will be created where? First node will be created. So look here, from here actually we can find out the propagation constant k is equal to 2 pi by lambda I can write. So I can find out a relationship between this various nodal points with respect to or in terms of wavelength. So which places the nodes will be created. Let us write this as x into 2 pi by lambda n plus half pi. Okay, so this will give you x is equal to lambda will go in the numerator, and so lambda by 2 n plus half. Okay, so this is actually the condition, or let me write in terms of this 2n plus 1 into lambda by 4, where n goes from 0 to 1, 2, 3, etc. Okay, natural numbers. Okay, so you can see the positions of zeros or zero amplitudes are called nodes. So these are the position of the nodes. So nodes, position of the nodes are obtained from this particular equation. What is that? That is 2n plus 1 I'm just to lambda by 4. Okay, this is the, I'm just removing this part because I have to do for nodes, antinodes also. So we have got the positions of nodes. We have got the positions for nodes. So where this n will be 0, 1, 2, like that. Okay. Now where the positions of positions. Okay, this can be again written in terms of velocity and see, this itself can be written as, so lambda, we know speed is into nu into lambda. So this expression can be written in terms of nu and speed of the wave and frequency also. Let us just replace this lambda. Lambda is equal to v by nu. Okay, if we replace here, look what we get. So x will be 2n plus 1. This factor will be as it is, and see this in place of lambda, if we write, this is v divided by 4 nu. Okay, 4 nu. So this is how we can find out a relationship between the frequency at each point. If we know the velocity, we can understand what frequency, what is the frequency of the wave produced at particular position. Okay, so this is v by 4x, like that. Okay. Okay, anyway, these things we'll discuss in this particular case when we talk about uh, various frequencies in string or organ pipe, etc. So this is the condition for or positions of the nodes. Similarly, positions of the antinodes we can find out. Antinodes we can find out from where? Here. If we put this as 1, if the amplitude is 1, when it happens? Amplitude 1, when it happens? When it is n pi. When the kx is n pi. Okay, in that case it will be maximum. So where n will be 0, 1, 2, etc. natural numbers. Obviously this will be the integer number. So if we put the k is equal to 2 pi by lambda again, and then find out the position of x, n pi, so pi goes off. Okay, so you'll get x is equal to n into lambda by 2. Okay, you'll get n into lambda by 2. In this case, you can see the position of the nodes will be x is equal to 0. If sorry, here n is equal to 0, 1, 2, etc. So first position is x is equal to 0. Okay, 0, there will be antinodes. Okay, obviously this is okay. So we'll have antinodes. So position of the maximum amplitudes are called antinodes. Clearly, antinodes are separated by. Okay, anyway, let us see the first position is this. Let me write the general formula here. N into lambda by 2. Okay, n into lambda by 2. So first position will be 0. Then if I say 1, then it will be second position of antinodes. And then it will be, if I write 2, then it will be lambda. If I write 3, then 3 by 2 lambda, etc. So this is how the positions of the antinodes are. Okay. And you can see if I take the difference between consecutive nodes or antinodes, here also the nodes position of the nodes will be, see if n is equal to 0, then it is n is equal to 0 means lambda by 4. N is equal to 1 means 3 lambda by 4. 3 lambda by 4. Then 2 means 5 lambda by 4, etc. you will get. Okay, 5 lambda by 4. Okay, so if you just take the difference between this, you can see there will be, see difference between, see consecutive antinodes 3 lambda by 4 suppose, and minus lambda by 4. If you just take the difference, you will get 2 lambda by 4, that is lambda by 2. So consecutive nodes are lambda by 2 distance away, and consecutive antinodes are also lambda by 2 distance away from each other. Okay, so this is what we can see from here. Okay, so this is, I think we have already covered the time to discuss these things. Standing waves. All right. Well, next day, so we have understood what is nodes, antinodes, what is standing wave, how standing waves created. So in the next day, that means tomorrow in the morning, I'll teach what is this, like how the standing wave created in the string, then in open organ pipe, what are the normal modes in closed, like one end closed pipe, one end open, like both ends open pipe, etc. And what is called beats, and what is the bit frequency, etc. we'll be discussing in the class tomorrow. Okay, all right, bye for today. Thank you for your presence.